Hello, in this video I shall discuss about the mapping of the Bitonic sorting network onto the interconnection networks, or how to map the Bitonic sorting algorithm onto the interconnection networks. As this is the old figure that I had taken into the last videos. All of these lecture materials are being covered with from the introduction to parallel computing by the Anand Rama. The previous videos as well as all of these videos are being referred, are being made in correspondence to that book. So, so if anyone want to read the text, that they can read the text. It is an excellent book, uh, which has explained the topics very well. I I'm not advertising because uh, uh, because that book has a number of errors also. So please read carefully because it has a lot of errors also. So here, so here you can be able to observe that uh, that the Bitonic sorting can be performed, uh, that the Bitonic sorting can be performed on the computers, and those computers are to be mapped onto the interconnection networks. So after each column, so the execution will take place on each column are to be actually implemented onto the interconnection networks or the underlying topology. The topology that I have discussed that are like the meshes, hypercubes, or any other trees, rings, etc. So the mapping of the pattern sorting algorithm into the parallel machines is done in such a way such that how they can be projected onto the underlying hardware, which is being arranged into the form of the hypercube, mesh, trees, uh, rings, linear arrays, KD meshes, and so on. Now, the topologies that I will discuss into this video and into the subsequent video is about the hypercube and the mesh. These are the two topologies that I should discuss here and here. Uh, into the Now in the pattern sorting network, I want to emphasize a few points that that by discussing about the pattern sorting network, uh, the the inputs are being provided with the help of the wires. The wires are the the wires are into the same number of the wires are there as the number of the elements into the sequence. So the same number of, so as the number of elements as the same number of wires are there. So uh, and with respect to these wires, the the parallel compare exchange operation or the parallel compare split operations have to take place since only one element is being transferred by a single wire. So into the old videos we have discussed basically the parallel compare exchange operation. Now but now there is the thing is that we want to we that earlier we have discussed about the logical implementation of the Bitonic sorting network. Now we have to implement into the processes which are running on some particular hardware. So this algorithm is to be mapped onto the processes which are running onto the nodes of the underlying topology. So these wires are to be replaced by the processes. How this replacement is to be done, that I shall discuss into the next slides. Now there is one more thing that is important, that how the elements are to be distributed onto the process. Either either I could distribute them one element per process, or I have to implement them as a multiple element per process. If into the into the last videos um, the scenario was that there were 16 different elements that are to be sorted. So 16 bytes have been taken. So that is the scenario as one element per process. But if we have the around 100,000 elements that are to be sorted, and uh, then it is a very cumbersome thing that if we will take 100,000 bytes to transfer the data. So the better thing, so the better thing is that I can take 100 bytes, and with respect to the each of the wire I will assign the 1,000 elements. Now these things are to be considered that I should discuss into the next slides. Now suppose that this is the following list that are to be sorted. It is basically the same list that that has been discussed into the earlier instances. Now recall that we have assigned these 16 elements. These 16 elements are being assigned as an input towards the Bitonic sorting network. That there are 16 wires, and with respect to the each 16 wires, each of the value is being assigned. So it is basically one element per process method is being given, such that at the wire 0 the value 10 is being assigned, at the wire 1 the value 20 is being assigned, the wire 2 the value 5 is being assigned, the wire 3 the value 9 is being assigned, the wire 4 the value 3 will be assigned, the value the wire 5 the value 8 is being assigned, and so on. And with respect to these same wires, the outputs are being transferred from the comparators. Either the increasing comparators are there or the decreasing comparators are there. The outputs are taken. The outputs are taken from these comparators. The outputs are being taken from these comparators, and then it's been transferred next uh, towards the next stage. So it is the first stage. So it is the first stage. The output of the first stage is being transferred with the help of wires towards the next stage, and in this way this whole process will continue. Now the question is that how to convert this wires based terminology into the processes. So here you can be able to see that there are 16 wires, and the values are being assigned to each of the wire. Then whatever the output is being generated, then whatever the output is being, then the wires are being assigned towards each of the values. It is the same thing that I have explained earlier, that the values are being put at each of the input for the comparators, and for each of the wire, some binary notation for the number of the wire is being assigned. With respect to the wire 0, the binary notation 00 is being assigned. Now, similarly, after the completion of the first stage, whatever the input is there, it is being transferred by the wires towards the next stage. It is also shown at here. So, since this second stage is composed of two steps, in which it is the step one, or it is the sub stage one, and it is the sub stage two. So it is having the stage one and the stage two. So the communication in between these two sub stages at the stage two are again to be performed with the help of the wires. So the wires are very much essential to transfer the values, to transfer the numbers from um, from the output of one of the comparator towards the input of the next comparator. So these wires play an important role, but the actual implementation which takes place onto the hardware is being done with respect to the processes. So, uh, so, uh, so, so the aim of this slide and the next slide is that we need to map these wires onto the processes, such that subsequently we can be able to say that these values can be marked um, are can also be assigned into the same manner onto the processes running onto the nodes of the underlying architecture. Now, it is the same thing that I have explained earlier, that the bytes are being used to transfer the individual output. That with respect to the third stage, it is having the three steps: step one, step two, step three. Now, again, in this case, they are playing an important role, and the output from one of the states is being transferred towards the next of the stages. So, in this way, we can be able to say that these bytes are acting as the processes. These wires are basically acting as the processes, and through these processes, the actual execution is taking place. Now we can be able to say that now in order to run onto the hardware, we have to replace these wires with the processes. Now, as I explained into the previous slide, that if we consider only one element per process scenario, that if there is only one element per process scenario, that if we have only 16 elements, and there are 16 wires are there, then I can be able to assign one element towards the one wire, or the one element towards the one process. But if we have the multiple elements per process, suppose likewise I taken the example of the 100,000 elements that are to be sorted with the 100 wires. So 1,000 elements are being given to the one of the wire. 1,000 next 1,000 elements are to be given to the next wire. Next 1,000 elements are to be given to the next wire as the input. And with respect to that, the execution takes place. And in the same way, these wires are to be mapped towards the processes. So, so now we have to understand the execution of these processes onto the different architecture, which is hypercube and the mesh. Now, how to assign these processes onto the interconnection networks? Uh, we, we know that all of these all that the wires have the integer values which are being assigned to them. Now, how to assign the processes towards each of them? Either I can be able to assign into some random order or into some predefined order. Uh, but 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 one thing is to be considered that whatever the order that we will choose, uh, either either I should assign into the processes in a random manner towards the wires or some predefined order, but the distance to transfer the values from the one process to the other process should be minimum. By that distance, I need to say that in order to perform the parallel compare exchange operation, the process Pi needs to transfer the data towards the process Pj, and the process Pj needs to transfer the data towards the process Pi. So if both of the processes are directly connected with each other, or they have an they have a common edge in between them, then the distance to transfer the data AI towards the process Pj is just one. And similarly, the distance to transfer the data from Pj towards the process Pi is just one. But if but if Pi has a neighbor Pk, and Pk is also adjacent with the Pj, and Pi and Pj are not connected with each other, then Pi and the Pj can be able to transfer the values to each other to the node Pk, to the node Pk, which is coming in between, and in this way the connection will be slowed down. The the, the the time to communicate increases. So we have to choose only that order in which the time to communicate the data from one of the process to the other process should remain minimum. Otherwise, the performance will be degraded. Performance will be degraded. So here you can be able to observe that the distance between the elements labeled with triple zero one, that this is the node number one, having the label as triple zero one in this four-dimensional hypercube. And if we want to transfer the data in between 0011 node of the hypercube, which is basically the node number three, then we can be directly be able to transfer the data in between these two nodes because the distance is one. With please understand that these all of these processes Pi, Pj, Pk are running onto the nodes of the hypercube. So here, if the parallel compare exchange operation takes place in between the node 1 and the node 3, the distance is just 1. But uh, suppose this is a scenario where I have taken the mesh. Suppose this particular node, the node number 0 and the node number and the node number 4 uh, are, are are taking part into the um, uh, um, compare exchange operation. So in that case, the node 0 has to transfer the element towards the node 4, and similarly the node 4 is to transfer the value towards the node 0. since node 4 and node 0 are not addition to each other, and both of them are simultaneously addition towards the node 7. So node 0 can be able to send the data towards the node 4 to the node 7, and the node 4 can also be able to send the data towards the node 0 towards the node 7, although it can be able to transfer the data towards other paths also, but it is the shortest path. But it is the shortest path in between 0 and 4, which is just 2. So so we have to assign the processes in such a manner that the distance will be minimum. So the ideal scenario for the minimum distance in hypercube is that, so the ideal for the hypercube is that the communication will take place into the into the um, into the right direction, into the right direction, such that the node 1 can be able to communicate uh, with the other dimension node. Um, we know that a four-dimensional hypercube consists of two instances of the three-dimensional hypercube, such that both of the instances can be distinguished with the first bit or the most significant bit of the um, hypercube. Those nodes differ with the most significant bit as the 0, while the most significant bit as the 1. Um, the communication should take place in between them, such that the distance will remain minimum. Similarly, with respect to the we can be able to say that it is the fourth dimension. If I want to communicate into the third dimension, the distance will remain minimum. If I want to communicate into the second dimension, the distance will remain minimum. So, in the same way, we can be able to discuss about the mesh. That into the old example, we have discussed that if this node is to communicate with this particular node, it has to transfer the information to this particular node. One thing is to be noted that the 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 flexibility with the hypercube cannot be uh, cannot be um, uh, cannot be inherited into the mesh, because the hypercube is having a different type of architecture, in which in which if in which a single node is attached um, um, with only one node in a single dimension, and and here this particular node is connected with two nodes in the same dimension, two nodes in the same dimension. Here, this node is connected with the two nodes in the different dimension, but this node is connected with two nodes into the same dimension. Similarly, this node is connected with this node as well as this node into the same dimension. So, we can be able to access the minimum value, um, so that we can be able to have a minimum distance of 1 into the hypercube, but with respect to the mesh, it cannot be possible. So, and hence we must be careful in assigning the processes to the interconnection networks, such that time will remain minimum, to transfer the data from one of the process running on one of the node towards the other of the process. So now the question is that how to assign the elements to processes, that I shall discuss into the next video.